So we graph both the f at x and the original function here. So I'm just kind of outlining it. I'll zoom out so we can kind of see it a bit more. So cameraing in here, we have the original f at x function, okay, that is written in red. So I'm going to just write it off the side. So the red is y is equal to f at x. And then the blue is y is equal to f at x to the negative 1, right? Or the reciprocal of that function. And those, it's hard to see, so we're going to actually camera it in here. And I'm actually going to get rid of the red. So I've erased the highlighters. So you can see that the red is the y is equal to f at x, and then the several blue portions are actually all the reciprocal. And when we learn how to graph reciprocals and rational functions, you're going to see why we ended up with essentially 3 different curves. But most importantly, I'm going to camera it in here. What we could see is that there are 1, 2, 3 invariant points, or places where they intersect, where the 2 functions intersect with each other. And most importantly, we can see that there are 2 at 1 and another 2 at negative 1 over here. So we know that for the reciprocal function, we know that there are always invariant points at 1 and negative 1. And the 1 and the negative 1 is going to be for this same x point. So when we go here, we could see that at 1, it's your x point of, and it looks like it's about 9.5, but we'll calculate and get the exact value. And at negative 1, it's the same x value here. So when you have 2 x-intercepts, that creates 4 points. So when it comes to reciprocal functions, remember that there's at least 2 invariant points, okay, when we take the reciprocal of an original function. However, when we're dealing with a quadratic, because it has 2 x's or 2 zeros, there's going to be 4 invariant points. So the steps that we use to solve these would be first to sub in into your quadratic equation, like over here, 1 and then negative 1 for y into the quadratic function. Then you're going to factor this quadratic equation for the x values. And since you're doing this twice, one for the value of 1 and one for the value of negative 1, you're going to end up getting 4 x's, and that would create the 4 invariant points. So we plug in negative 1 for the y value of the invariant point, which we know is negative 1 and 1. And then we set this equation to 0 over here. And then what I do is I use the quadratic formula because often that's the only formula that's going to be open up to decimals and anything that's a little bit obscure to calculate or that won't take so long. And so we see that at negative 1, I have, well, the following invariant points. So we got negative 1.9 and negative 1. And then we also have 8.9 and negative 1. So again, I've plugged in my y value here, and we're just going to now factor your x squared minus 7x minus 19. Again, I'm going to use the quadratic formula, and let's see what we get as x squared. So again, plugging all the values in the quadratic formula, we end up getting our 2 x's at negative 2.09 and 9.09. So then going back to here, we would say that there's, again, invariant points at negative 2.09 and 1, and then as well at 9.09 and 1. And so here are all the invariant points of this quadratic reciprocal if we were to solve for it algebraically. So for the last example here, we're going to find the invariant points of the certain transformations in A and B for f at x is equal to x squared minus 8x plus 13. So when we say that y is equal to negative f at x, that refers to the a value, right? So a value is everything outside the bracket over here. So that would be a vertical reflection. And when we have a vertical reflection, that is going to be on the y-axis, or on the x-axis, I should say. So your invariant points will be on the x-axis. So when we graph the two, we have here the original function in red and then the reflected along the x-axis in blue. And we could see that there are two invariant points right where the x originally was in the graph. So 2.268 and 0 and 5.732 and 0. Now, how do we prove that algebraically? Well, we do the following. So, of course, if we plugged both of the values into the quadratic formula, we'd factor for those zeros, we would get 2.268 and 5.732, which is, when we look, is equivalent to the graph, right? If I go here and I go to the x-intercepts, we could see that it's 2.268 and 0 and 5.732 and 0. And that's where the two graphs intersect, which would be the invariant points. Now, because we're getting the inverse of a quadratic, we know that there's going to be 4 invariant points. Now, here's the part that's going to be different. When it's a quadratic, or the reciprocal of a quadratic, we know that there are 2 invariant points for y. We have an invariant point at x and 1, and x and negative 1. And since we have 2 x variables, that means that there'll be 2 for each of these, giving us a total of 4. So the way we're going to do this is, we're going to now insert y equals 1 into the quadratic. So inserting the 1 into the quadratic and then setting it to 0, we get x squared y is 8x plus 12. And so then what we're going to do is we're going to factor this value here. Okay, so I factored the quadratic at y equals 1, and I end up getting x is equal to 2 and x is equal to 6, because remember we set each of these brackets to 0. So what that means is, when I start writing my invariant points, and I'm going to do this to the side, so I'm going to write IP, that is going to be, one of them is going to be at 2 and 1, and the other invariant point is at 6 and 1. Now we're going to do the same thing, but instead of putting y is equal to 1, we're going to write y is equal to negative 1. Now what we're going to do with this new function is we're going to factor this function, and again we could use the formula in the previous question here, or you could factor it using decomposition. Either way is fine. So factor this, and let's see what our x values are. And when we factor this, we get x is equal to 2.586 and x is equal to 5.414. And so we're going to say that there's another set of invariant points at 2.586 and negative 1, and then 5.414 and negative 1. Altogether giving us, as we mentioned, a total of 4 invariant points.